Hello everyone. My name is Lenka. I am a PhD candidate at the University of Bristol, and I am conducting a research in advanced quantitative geography under the supervision of Dr. Levi. Today, I want to talk to you through my research and some of its preliminary results. I will give you a quick 1-minute introduction of the basics, just to make sure we are on the same boat. And then I'll guide you through the theoretical background and introduce the aims of my research. Lastly, I will talk about the preliminary results that involve some concepts of a graph theory. So first, let me explain some basics. What is the origin and destination data and where they can be found? Those data are referred to interaction in a space, and they are made from 3 base variables, which is the unique ID of the origin, the unique ID of the destination, and then the volume of the interaction. For example, if we take a migration data in Europe, the origin and destination's ID would be the names of the countries, and the volume of the interaction would be count of the people that migrated between those places. Such a flow data can be found almost everywhere: transport, biology, geography, but also in virtual spaces, such as the social networks or social media networks. The most common approaches to model these data are a spatial interaction model. Those are regression-based models based on the analogy of the gravity models, which takes the information about the masses on the origin and the destination node, and then the distance between the nodes to predict the flow volume between the nodes. Here, the distances is the primary indicator of the relationship between the nodes. The spatial interaction models have been developed in early 20th century and has been successfully used in econometrics. For example, Haf's model, which you probably know, is a spatial interaction model that estimates patronization of the retail centers and deliver the probabilities of consumers shopping in each origin or destination. The gravity model analogy, though, has several theoretical gaps that has caused the accuracy of the model to be very low. A typically very good spatial interaction model would reach around 70 to 80% accuracy. The performance of the spatial interaction models has been a continuous discussion in the academia for the past 100 years. And there is many reasons why those models does not perform as good as we want them. But perhaps the main problem is generally the fact that we are trying to use an analogy of a physical model to explain a phenomena that is not as much physical. The biggest part of the discussion is the distance decay function, which represents the decay of interaction in space. Now, let me explain the main problems arising with the spatial interaction models. Firstly, the distance decay function, which generally consists of one mathematical function, which is usually parallel or exponential-based function. And this one function represents the spatial deterrence in all directions in the same way, which in reality is highly unlikely unless we're working in a completely homogeneous space. Furthermore, we know that the different distance decay functions define a different nature of the spatial relationship. So using one function to represent all the interaction is rather naive idea. Secondly, although there is a strong evidence that the distance is related to interaction deterrence in a space, there is an ongoing discussion on how it is related and on the strength of the relationship. In the last century, scientists from various fields noticed a significant weakening of the effect of the distance with the development of new technologies such as the fast internet, fast transport, and a lower cost of the traveling as well. On the other side, some argue that the complete depth of the distance is irrelevant and that its effect is always present in some degree. The gravity models also assume that all the people behave the same way, but one of the major quantitative findings of an urban spatial decision process is that human travel patterns are far more complex than simple frequency of the trips or distances, and that the spatial decision-making vary by each individual. The only similarities in the movement patterns of humans we found so far are the socio-economic properties of individuals and their trip properties. Consequently, academics began to question the existence and the role of the spatial structure in the spatial interaction, and it was found that the spatial structure is related to physical and the social landscapes, landscape connectivity and accessibility, spatial autocorrelation amongst the origin, destinations, and the flows themselves, but also some randomness. This implies that every unique type of interaction have a unique spatial interaction and spatial structure. Since 1970s, when the spatial structure debate was brought up on light, we've seen many methodological directions to the spatial interaction models evolve into. For every specific problem and specific type of interaction, there has been found a specific solution. The most promising so far has been the use of the spatial autoregressive or spatial effect models, which seems to capture the spatial structure generally well. However, their big limitation is the difficulty to interpret them and directly compare them with other methods. Furthermore, with the recent advances in the technology, we have also seen an application of neural networks to spatial interaction, which happened to be very successful in capturing the flow dynamics. In fact, already Openshaw in 1998 argued that advanced machine learning methods, such as the neural networks, are more suitable for modeling spatial interactions. That might be because its architecture, which consists of layers and nodes, is very similar to that one of flow network, but also because that the neural network is able to account for a non-linearity and detect more complex patterns that statistical learning fails to account for. However, we still need a research that investigates the spatial structure in machine learning models. In result, most of the interactions based on the traditional models are misspecified and face serious overestimation. More importantly, the role and the form of spatial structure is still unsure, as it is much more complex than we have thought. So my research questions are, if the advanced methods, such as the neural networks, are better than the classical approaches, how do they capture the dynamics of the urban flow? How can I measure which model captures the spatial structure the best? What actually is the difference between the traditional and machine learning models? And how does this change if we introduce spatial effects to those models? Today, I would like to talk more about the first point and introduce how we can measure the spatial structure using ideas from a graph theory. Well, there are several methods used to evaluate the predictive performance of the spatial interaction models. Some are more traditional, such as the R-squared or root mean square error, and some are less traditional but more suitable for the flow data, such as the Sorensen index or common part of the commuters. Although these methods shows us clearly the predictive accuracy of the models, they do not tell us anything about the spatial structure of the flows. We want to take the measures of a graph structure as a validation method to enhance the traditional predictive measures and provide flexible framework for inspecting the spatial structure of the flow network. In the rest of these slides, I will explain in detail what does it mean and how does it work. A graph theory is a mathematical field that studies a graphed object, which are network structures defined by the nodes and the edges that connect the nodes. And this is exactly what the interaction flows are. It's a bunch of places connected by flows. Therefore, if we are able to translate the flows into the graph, we can then use the measures of the graph structure to inspect the structures of the flow network. The main principles of the graph measures is to describe the importance of the nodes within the network landscape. In general, we talk about the importance of the node as a centrality of the node, within the network. However, what counts as central is heavily dependent on the context and application. I will give you an example using the intra-migration flows in England and Wales, for which nodes represents the local authorities and the edges are the volume of people moving between those places. One of the most used measures is the degree centrality, which counts the number of the incoming or outgoing flows into local authority. From those, we can observe that the most important places for the incoming movers are North Somerset or parts of the Lancashire. On the other side, we see an increased importance for movers that leave the authorities in Norfolk or North Hampshire. But from all the graph measures, there is one that actually stands out the most, and it's the famous PageRank, which is an algorithm used by research by the search engines, such as Google or Yahoo, to find the most relevant pages to a certain query. This iterative algorithm identifies the importance of the node based on the number of the flows, their propensity, the flow volume, and the importance of the connected nodes. And this precisely makes the PageRank very desirable measure of a structure for the urban flow networks, as it assigns the high importance to a place which has overall high connectivity. And in our example, those are, for example, Sevenoaks, then the Northwest Leicestershire and the local authority of Wyre. So how do we use the node importance, or the centrality, to evaluate which model is better? Well, we can simply compare the node importance of the observed flow networks and the flow networks that are constructed from the prediction of each model. For example, here you can see the importance of local authorities based on the observed data, based on the prediction from a basic spatial interaction model, and based on a prediction from extreme gradient boosting model, using the same formula, obviously. Although the pattern seems to be similar at the first glance, actually, when we take the difference between the observed and the predicted importance, we notice that there is also a pattern in those differences. In all of the areas, the importance seems to be overpredicted, except those areas that indicate a very high importance in the observed flow network. Basically, the more important the local authority is in the observed network, the worse is the model in capturing this property. And here we are only talking about a very generic traditional type of network in which we can observe both inflows and the outflows. However, if we take a different, more specific network, the results are different. Here is an example of a bipartite graph, which is the network where we can only observe the flows in one direction of flows that go from origin to the destination only. In that case, any importance either above or below average is over or underestimated, and we even get this horrifying prediction of no importance whatsoever. This basically means that the model is failing to retain the structure of the flow network, even more so in very specific types of networks. You need to remember, though, that we did not account for any spatial structure in the models. So the model don't see the spatial structure directly yet. Yet the XGBoost model is visibly better in retaining the structure, even in the non-traditional type of a network. So what I want you to take out from this presentation is that although the spatial structure of the origin-destination flows has been rather ignored in the literature so far, it is necessary to incorporate its validation into the prediction framework for its models in order to provide better understanding of both the flow network structure and the models used for its prediction. The biggest advantage of this method is that it can be used to compare the models, the model performances across the different frameworks. Doing so, we have found that the advanced modeling techniques, in our case, the gradient-based model, outperform the traditional models in retaining the flow network structure, especially in non-traditional, very specific type of networks. The next step of my research is firstly to use the spatial structure validation method to assess the performance of a neural network spatial interaction model, and secondly to compare how does these models perform in comparison with its spatial effect version if we actually account for the spatial structure. So thank you for listening today. There's a bunch of references if you're interested, and we are ready for a question.
Thanks very much, Lenka, for that presentation and for staying on time. It's really interesting work as well. So again, I'll open the floor for questions. And if anybody has any, they can type them in the box there, and I'll present them then to Lenka. In the meantime, I just have a question there about your next steps. So you're going to look at neural networks. What's your intuition for how it's going to, what they're going to show us or do for us?
So according to the literature, it seems like they're going to be a major improvement because they can detect the patterns without seeing the patterns directly. So we'll see how it goes, but I have high hopes.
Okay, and have you designed the start of that yet, or how you're going to go about it?
Not yet. That's the very next step after the September, where I'm going to be submitting my progress report after the first year of PhD. So I'm going to get there.
Okay, good luck with the progress report, and we look forward to hearing about how the neural networks work out. So there's a question there. So thanking you for your presentation. And what are the important features that predict the spatial interaction in your study?
That's a good question, thank you. So the spatial interaction models are based on the basic gravity models, which consist from three variables, and that's the distance between the places, and then any kind of like a mass variable for the origin and for the destination. For example, in the inter-migration flows that I presented here, the mass variables would be population sizes at the origin local authority or the destination authority, and the distance would be a great circle distance. But obviously, depending on a type of a network, you can change these variables, such as a network that is based on the city. Probably something like a path distance that goes along the roads is more suitable. And those are just the basics, a basic work of the model. Additionally, it is possible to feed in more variables defining it, but we are looking at the base of it.
Okay, thanks for that answer. So there are a couple more questions coming in now. So the first one is, how do you deal with spatial dependence, heterogeneity, and scale effects in the OD flow data?
That's a very good question, thank you. Honestly, each network has a different properties. It might be that it has them all, and it doesn't need to have any, or it has just one of those. And I'm not sure yet how I'm going to deal with it. But I want to the first purpose of trying to validate the spatial structure is detect those kind of things, and looking at those, looking at the spatial dependence, trying to find out if there is any a scaling issue. So it's work in progress, and thank you for that question.
Okay, thank you for the answer. So there's another question. So again, thank you for the presentation. Are you also considering how your flow networks are changing over time? For example, a spatial structure may change depending on when your data were collected. For migration, you'll have a different network at every census. For retail, you would have a different structure normally than you would have during the lockdown when only essential shops are open. So do you consider time along with space and how your network changes through time? It's a long question with some examples in there.
That's okay. Very good question. Thank you.
I guess it's how do you consider time?
Yeah, that's completely true. The network's changing over time, but the data I have for the migration flows, they are published yearly. So we only have one estimate of how many people move between the two regions per year. And although I have the data goes far into 2012, the methodology they create the data is actually changing every 2 years. And because I don't have enough stable data for establishing a time forecasting, and I only work with like 1 or 2 years, I don't go that direction. And for me, the spatial structure is the main issue I'm working on, rather than the looking at both the time aspect as well as the spatial one, because that would be another whole dimension of the problem. Thank you.
Yes, I think it would add to the complexity of it. So if there are any other questions, you can type them in there. In the meantime, you mentioned PageRank.
Yeah.
Could you just tell me what you did with that, or what the connection to that was?
Well, the PageRank is basically a link or centrality kind of algorithm that calculates what is the importance of the node within the network. So, and the advantage of it is that it basically accounts for accessibility and connectivity of the nodes. So the PageRank, although it's mainly used for, as I said, ranking the pages on a website, it seems to be so well fitted to our issue of the spatial structure in the flow network. So there is not much, I haven't seen anybody using it so far. Maybe I have seen one paper with the suggestion, oh, this could be good to use for this purpose. And so I need to build a more of the theoretical base for this, if that answered your question.
Yeah, I'm just interested in a bit more about it. That's good. Has anybody else got any questions there? Yeah, it's hard to explain it in a minute, I understand.
Yeah, as well as the PageRank is quite complicated algorithm that is iterative, and it changes like every time you do the iteration. So it's hard to explain that as well. I will suggest look on a Google and try to find out, and then let me know on Twitter if you got it.